Okay, I really will do my best and try to do my best to stop at exactly the right time. So 1:45. But I still have made the experience that the moment I sort of approach the last slide, everybody starts packing and they don't listen. So I've made now the decision to start with my last slide. Yeah? So this is the last slide of the lecture, and it's about what should you do with the remaining day until you have the lecture tomorrow, and what's coming for the rest of the week. So until tomorrow, honestly, I want you to practice Schnapsen. Please go out and play. Yeah? Maybe you have to buy cards. So they're not that expensive. It's an investment worth doing for this course. Find someone who can't run away or who loves you, and try to play Schnapsen with this person. It is really nice. Yeah? Because I will try to explain it tomorrow. I will explain a little bit the ideas, but it's different when someone explains the rules of a game as opposed to when you play the game yourself. So please play it, and it will help you to understand what I explain, and that's, I think, the most important thing, but also help you to devise strategies and so forth next week. So, then there is stuff already published on Canvas. It's called additional material. There is video lectures that you can watch. There is a reader that is last year's reader, but all the material in there is still relevant. So I might reshuffle it, I might add some material, but everything in the reader is relevant. And there is some authorized copies from the book AI, A Modern Introduction, or something like this, from Russell and Norvig. It's the Bible of AI. And the copies in there really describe the state space problems, the search, and so forth in the best way, I think, that has been written up. And this is really also the material that I follow here. So look at this, start reading today. Register your groups on Canvas, and then read the material, watch the videos, and play Schnapsen. Yeah? That's all for today. I'm going to talk about state spaces and search now. Tomorrow we move from the simple search that we do today to informed search, and also to adversarial search. This is very fast, it's very condensed, because I want you tomorrow also to start looking at the code and at the programs, so that you can maybe already start with the programming of maybe min-max algorithm and understand how these algorithms works and how the game engine works. And on Wednesday I will do more about the adversarial search, particularly the alpha-beta pruning, which is the optimization. And we look into how can we now really play the full game of Schnapsen using adversarial search techniques with Monte Carlo sampling and min-max. That's basically the topic for the first week. And then on Thursday, I will cover more of the basics of AI, agents, and so forth. Material that I now skip because I really want you to have the hands-on experience as quickly as possible. So this is the course overview, and I think it really is mostly about decision making. So you want an intelligent agent to make the right decisions at the right moment in time. It's very difficult to decide what is the right thing to do, but I mean, this is what it's about. We want to do it in a generic way, and we want to do it so that it doesn't only work for Schnapsen, but the same things that you implement in your bots can also be applied to other games. So min-max is generic techniques that you can apply for Schnapsen, but you can also apply it to Go or any other game where you have an opponent. It should be very efficient, because you will see that these problems, even for a simple game as Schnapsen, are extremely complex. It should be simple, it should be correct. The framework should be well understood, so we should understand the complexity of the problems and so forth. and it should be generic, as I said, so re-applicable to other domains and other problems. And then I've built this little pyramid here. So we start with systematically finding all the possible solutions to a state space problem. That's today. Tomorrow we find the best decisions with some informed search. So we have some human knowledge that helps us find these solutions using some heuristics, some estimate of, some guesstimate of what the best solution would probably be. That's going to be tomorrow. And also tomorrow we start looking at the multi-agent setting where we have an opponent to play. So today it's only single player, single person, single agent. Tomorrow we move to the 2 players and multi-players. And then next week we have the best decision with formalized knowledge. And then in the 3rd week we have the adaptive, the learning. So let's dive in and start really with the theory. The topic is state space search. So let's first think of how can we represent complex problems as state space problems. So state and transitions between states. That's the basic idea. So here's an even more simple example than Schnapsen. And I put a question mark because it will turn out on Wednesday that Schnapsen is everything but simple. So it's really as complicated. This one is really simple. So basically what we have is a Hoover, an intelligent Hoover. We all want to have this. That works in 2 rooms and it can only do 3 things. So it's not very intelligent. It can move from room 1 to room 2 and it can Hoover. It can clean. That's all. So then the question is, can we program some algorithm where the Hoover moves in an intelligent way between these rooms so that at the end it has cleaned all the house? And it can sense whether there is some dirt, so then it knows that it should Hoover or not. So it's very, very simple, basic. But still, if you want to write a program that does this, you have many things to take into account. So you should sense, where am I? How do I get from room 1 to room 2? How do I measure whether there's dirt? How do I, how fast do I have to go? How slow do I have to go? So the real world is absurdly complicated and complex. And that's why we have, when we talk about the decision making of which of these 3 actions my robot has, which should it take, we should also have a very simplified framework for abstraction over this problem. So we have to simplify our environment, our world, so that we can really look at the decision problem at the moment when it's needed. So each of the states that we will see describe a real set of states in the real world. And then we have action, so we can move from left to right. And this is an abstraction over very complex operation where the thing has to start rolling with its legs, with the wheels, and then it has to sort of maneuver through the door. We all ignore that. We abstract over it. We take a subset of go from left to go to right. And then a solution is a set of real paths, so the real solutions, so that we can then translate the decision that we've taken into an action that we take. And there might be different state space representations. So this is an example of the vacuum cleaner world where you have a state, which is this one. So both rooms are clean. The thing can move to the left, and it ends up in the same state because it's already on the left. So there's nowhere else on the left to go. It can move to the right. That's this movement. So then after doing this, performing this action, it ends in this state. It can clean, and then nothing changes because it's already clean. And I wanted to start with this one up there, but I have no pointer on this device. So you see that here there is dirt. When you clean, the Hoover is still on the same room, but now it's clean. And basically, this diagram, this abstraction, gives you all the possible combinations of of where the Hoover is, whether there's dirt, which action it takes, and in which new position, its new interpretation of the world it gets to. This is one possible state space representation for Hoover in two rooms. So now the problem-solving agent knows that some of these states that it can be in has a solution to its problem. So, for example, the rooms are clean. So this would be these two states. So the question is, how do we get from the top left position to one of those goal states? First of all, we have to think, how do we represent the world in these states anyway? And as I said, we have to abstract over particular information that we consider not relevant for the decision process. And then, what are the actions to get from one state to another? And in a later stage, we can also think of what is the cost of going from A to B, because that's relevant if we have a restricted resources. So these are questions when we build a state space representation of a problem in some kind of environment in which our intelligent agent can then operate in. We have to define what is the goal. So the goal in this case would be the two states where the rooms are clean. And then the only problem is to get from the position that we're in, from the state that we are in, to a state that fulfills the goal conditions. And then once we've found a path, choose the best sequence of actions to get from the position we're in to the goal state, we have a sequence of action that we can perform, and then the Hoover can move. You can think of many, many different examples. So and robot assembly, you see already that you have many degrees of freedom in this arm that moves and does some things with a car assembly or whatever. So you need to abstract over it. You can, for example, say rotate by 45 degrees, but you can say rotate as one of the actions. And if that's good enough for your decision procedure, then you should have as simple as possible state space representation. And if you think about this example a bit more, you can really think of different abstractions that might be useful. So it might be lift the block as the only action that it takes. And then if that solves the problem, fair enough. But if you want more complex things, you need to take into account all these degrees of freedom of this robot arm. So start with a concrete problem, formulate an abstract algorithmic representation of it. So you need to formulate states, you need to formulate actions to get from one state to another. And then you need to define a clear and algorithmic goal. So I need to get to these two states on the bottom where the rooms are clean. Find the solution and then execute the plan that you found, and that would then be move and clean according to the abstract solution. You would still have to implement the decision of the Hoover going from room A to room B, but that's a different problem. So we've abstracted away from this problem. This is an example that I'm going to show you more often in this lecture, and that is a traveling problem in Romania. Are there any Romanian people in the room? There's always an awkward moment because I'm sort of violating the Romanian city names. Good, so I just can do whatever I want. So the task is to get from this place Arad to the city of Bucharest. And what we know is that there is some road or train connection between different cities in Romania and the distance that it takes. And the task is if I want to come from Arad to Bucharest as quickly as possible, what do I have to do? And then we could obviously start looking at, okay, I have a car that needs to, and if you really get into the details of the street, and then there might be other cars, and it might be, so you can, if you really take into account the real complexity of the world, you will never be able to do it unless you have a sort of the Google resources to do an intelligent car, and even that. But what we can do is that we abstract over it, we say we address the problem of what is the shortest path to get from Arad to Bucharest if we have these assumptions formalized. Yeah? So in this case, the state representation is, I have a flight tomorrow in Bucharest, I get from Arad, and my states are cities or various cities. My actions are to drive between the cities. And in the formal sense, that is move between the states. I have a concrete algorithmic goal, and that is be in the state that is written with Bucharest. The solution is really the sequence of cities that I have to take to get from Arad to Bucharest. And then at the end, I have to execute the plan, and that is to buy the tickets or drive or whatever way I travel from Arad to Bucharest. And that would then be via these cities. And how to find this sequence is what we're going to do in the next slide. So how does that relate to the games? In the games, it's exactly the same. So we look at a representation, and the nice thing in chess, you have already the representation of the chessboard with the figures, where they are located, and so forth. And basically, an action that you can take is move your pawn, or you move your king, or move the queen. And then if you have such a position, white has, I think, 10 figures, then it probably has about 20 different options of moving the figures. So we have a state space representation that's a tree. Maybe it can become a graph if you go back to the same constellation, but in a way we have this representation with loads and loads and loads and loads of connections. And here is, I think, you start seeing the problem why it's difficult to get from a state to one of those states that might be winning state in chess. So here is where really the algorithmic complexity comes into play. In Schnapsen we do exactly the same. So Schnapsen is a two-player game, but I want to look at a simplified version where we have one player with both sets of cards in the hands and playing to optimize her own success. So there's only one player with two hands, H1 and H2, of 5 cards each. P plays a card from the first pile, and then a card from the other pile, and then it's the standard Schnapsen rules that are applied, and the player P succeeds if she has 33 points or more. So tomorrow we'll tackle the problem when this second move is an opponent who tries to sort of destroy my strategy. Here, I try to optimize my strategy. I'm only one player. I play with myself. Completely boring game, but still. So this is how it looks. We have an opponent X, which is normally the max player, and an opponent I, which is a min player. We'll see that tomorrow. So that's the min-max algorithm that we see tomorrow. At the moment, these are my 10 cards that I have in my hand. And what I want to do is I want to play the game and as quickly as possible get to 33 points. So basically the starting player has 5 cards that she can play, and then the opponent, or in this case it's the same person, has more options. So you have to, if a spade is played in the second phase of Schnapsen, you have to play the same color of the cards. So this player can only play one card. Only if the heart is played, she can play 3 cards. Yeah? So this is a very simplified game where the first player has 5 options, and then when she plays the other hand, she only has one, or in the worst case, 3 things. And then we can go on. Then it's the first hand again that we play, and we have 4 options only left. And for each of the possibilities of the second hand, we have 4 more again. Yeah? And then somewhere around here, maybe that we don't have any cards left, and then we finish and we win. We have more than 33 points or not, and find a solution or not. So now comes a question, and now I want you to take out your Kahoot thingy again, and I hope that it still works. I'm not sure whether you're kicked out. That was the sort of person who answered quickest. Anyway, it doesn't really matter. Now, you have 2 minutes, so that really gives you time. So how many states? Is it gone? Sorry. I will start again. Sorry, I'm sorry, we have to register again. That gives you time to think. So the question is, how many states do you think this tree that I just showed you will have maximally? It should come now. Yep. And as you did before, don't worry about the names. That's not the point. So you now have 2 minutes to think of how many of those states that I showed you in this very simple game there might be. So we start with 5 cards in one hand and 5 in another. Good there? But there are more coming. Nice. Okay. So I'm going to skip this. Don't answer. Oh, okay. I want to know whether it's the same answer. Oh, good. Excellent. I'm not asking the 13 people who like the game. So, next question. How funny. Now it's how many game states? And now you have 2 minutes. How many game states do you think there are? Maximally. Now I completely underestimated you, so you're far better than I thought. Can the remaining 3 people please do something? Then we don't have to wait for a minute. 1 more, 2 more. Okay. Okay. I think you all are. Oh, here we are. Hey. That's good. Is there anybody in the room? Is there anybody in the room who did not guess? Because this is a completely random distribution of just people guessing randomly. Yeah, so it's yes, you 2 people. We have 2 people. So there was little time to calculate, but you could have calculated it. Because suppose we have to it wouldn't work for these cards, but it might be that you have always the maximal option. So if the one has only hearts and the other has only spades, the second player can always play what she wants. Yeah? So in the first round, we have 5 options for player X. And player Y can play 5 cards. So there are 4 cards now left. Yeah? Player I can also play 4 cards. And you see where this is going. This is basically the number of states we have is 5 faculty times 5 faculty. Yes? Which is 120 times 120. The tension rises, and it's green is the right one. Yes? Yes? Sorry? Yeah, then it completely changed. We're going to talk about this later. But in this game, maybe that explains the 60% who got it wrong. But in the case where you really play the card and there are fewer cards every move, this is the answer. the complexity, if you draw a card, particularly if there's uncertainty involved, is far, far bigger, and we're going to discuss that tomorrow. So I think there is another question. No, Nickard is good. Excellent. If you pretend to be my son or whatever, please get my name right. It's just a request. You don't know how many emails I get. Dear Slobach. Yes. So, okay. So this is too fast. Stop. Where can I stop? I can't stop. Okay. I have no idea how to stop this, so don't answer. It's, yeah. Oh, excellent. I told you it was a random distribution. Okay, we skipped that later because we don't have any time anyway. I'm sure Schlobach Jr. did very well again. So, now we have seen these search spaces, these state spaces, and the question is, I mean, this is an extremely simple game. This is an extremely simple game, and we have already 15,000 nodes that we have to search through. So now the question is, how do we find the first, or maybe even more importantly, how do we find the best solution? Or find all the solutions. So there might be a solution here, there might be a solution here, here somewhere. How do we find it? And how do we find it as fast as possible and with as little memory as possible? So, as I said before, we are in one of those states and we want to move down here. That's very tricky. And the basic search algorithm is we start from the position we are in and we know which actions we can take. And basically, we build a search tree to get explicitly building a search tree where the root is the initial state, and we create nodes and leaves. We create nodes for every state that we get from an action. And if we can't do any more actions, then we land in a leaf of the tree. So this is the example. This is the algorithm. That's a pseudocode that you can read at home. But the idea is very, very simple. We initialize the search tree to contain the initial state. And I use the Arad example, so that's the state I'm in, the city I'm in the state representation. And then I choose leaf nodes to expand according to the actions that I can take. And if the node, if there is no node left, then I'm done. If the node contains the goal, then I have found a solution. And otherwise, I have to expand the node again, and I do this recursively in a build a tree. Yeah? So this is the moment where it's decided on which nodes to add to my algorithm, to my search tree. Yeah? So one last thing about this sort of on a generic level, we have to be very aware of that we have, on the one hand, we have a data structure for building this search, which is the state space representation, and we have we have the representation of the world, which is the state spaces, and we have the representation of the search, how we produce it. So when I talk about the nodes, then I talk about the search, and when I talk about the states, I talk about the representation of the real world. It's an interesting distinction, an important distinction to make. So now the question is, how do we do this expand procedure? And this decides on how to do the search. We have to look at different properties of these algorithms. We have to look at completeness. Does it find all the solutions? Does it find the solutions if there exists one? Does it always find the least cost one, the best solution? That's optimality. We have time complexity. How many nodes does it create? How long does it take to create those nodes? Space complexity. How many nodes do I have to keep in memory? Because this can blow up very easily. And they're measured, so they're measurable, they're well understood. So we need a number of letters for this. So we have the B is the maximum branching factor. So that is the amount of possible choices I have. So that is 5 in this case. I have a branching factor of 5 in each of these states. to the next round where I have a branching factor of 4. And the B is the average branching factor of the maximum branching factor, sorry, I have to say, the maximum branching factor for my choices. So how many choices do I have at the possible states? So if you have a chessboard with 10 different figures, they can all move in many different directions. You have a branching factor of around 20, 25 maybe. We have a maximal depth. That's if you look at the best solution, then what is the distance between the root and this tree? That's the depth. And then we have the maximal depth of the state space, which might be infinite. So if you have a loop, if you go back and forth, then it might be infinite. So that gives them a mathematical framework for judging the quality of the algorithms. And we're looking into today, I tried to get you some overview of a breadth first, depth first, and iterative deepening search. I might not get to iterative deepening and do that on Friday instead. But depth first, breadth first, you should really see and understand. And they will also be practiced in the working groups. So the working groups are for the theoretical material that I explain here, that I go through very fast. And if you want more time, you can really practice them on Thursday or Friday in your working group. So the fringe is a FIFO queue. Does that sound understandable for anybody? First in, first out, yes. So the fringe is basically the storage of the nodes that I still have to explore. So basically, that's what is the basic principle of a queue. You have an element that you put in here, and you always put the new element at the end. And when you take one out, you take the first one out, and that is how your queue works as your data structure. And if you do this, if you store your nodes in a FIFO, in a queue, then this is the behavior that you get in your search. You start with the top one, you evaluate the successors, you put them at the end of the queue. So B and C doesn't really matter. So we start with A, and whether to do B or C doesn't really matter, but we start left on the left-hand side. You put them in, this one has gone, we have treated it, so now the next one we treat is the B. Yeah? So this is why the arrow is there, and we look at all the possible actions that one could take in B, and we add what is there to the end of the queue. Yeah? Then we look at B, we've done that, we look at C, that gives us 2 more nodes if we evaluate it, and that is F and G. Basically, that always gives us the same, all the nodes on one level of the search tree. Yeah? And that's why this is called breadth first search. So you go into the breadth of the tree. Yeah? So BF search, this is how you implement breadth first search, by just adding things to a queue and taking out the first one, expanding it, and then you get the full breadth of the tree. What is the properties? It's complete. Yes, it always finds the right answer because it looks at all the nodes on one level after the next. There is, if the shallowest node is at some finite depth D, there might be examples where there's infinite breadth, infinite depth, and then it might be difficult, but under these conditions, if B is finite, if the branching factor is finite, you will find a solution. It is very complex, but that is a bit part of the problem. So if the root has B successors, so that's a branching factor, then we have to add B squared at the next level, B to the power of 3, and so forth, up to the depth of D, where we'll find the solution, which basically means that we have a complexity in the order, this is this notation of the order notation, in the order of B to the power of D plus 1. So depending on the depth, you go very, very deep. So if you have a branching like we have a 5, and you say we go 5 levels low, then we go to the 5 to the power of 5, or let's say we want to look ahead 7 levels, then we get to this, and this is a huge number. Don't underestimate. It's far smaller than this number. And the difference is that, as was mentioned here, in the example that I gave with the Schnapsen caricature, the number of options reduced because we didn't take any cards from the pile. But if you take cards from the pile, this is your complexity. It's huge. Yeah? What about the space complexity? Now it really gets worse, gets really bad, because each of the nodes has to be retained in memory, apart from the ones that we have sort of can delete because we have expanded them. But that means we have the full breadth of the tree in our memory. And it always finds the least cost solution because it really goes step by step. But the problem is really the space consumption. The time doesn't really matter that much because we can have efficient algorithms. We can wait a bit. We can wait a couple of years to get an answer to our game. But the problem is that if this is a very simple example where you have, I think, just a branching of 2, and then you do the exponential depth. And it basically means that if you go to a level of 14 deep, then you have 2 to the power of 15 nodes, and that would take an exabyte of memory, which is really prohibitive at the moment. So we have to think about it. I already got answers to this question, so we don't have to do it. If you go down the breadth first in Schnapsen, you need to have everything in memory. What is the number of nodes that you would maximally have in memory? It's the same number that we had just looked at. The question is, how deep would you have to go, I think? And basically, you would have to go to the lowest level where you find a solution so that you then can return the answer as an answer to winning this game sufficiently. So that was one data structure where we basically start level by level of the tree, looking at all the options. Big problem is that it doesn't really work in terms of memory. So the alternative is, of course, the LIFO. And the LIFO is a stack. And the idea of a stack is this. You put things on top, and you take things from the top out again. So we put A in, and we put A out again because we use it, and then we put B and C in again. So up to now, not much has changed. But now we expand B, so C still remains in the stack, and we add the new ones, D and E. And now we take the top one out. So this is now the difference. We don't take C out again, but we take the top one out. So we go on with D and expand D. So we get the 2 nodes H and I, which we add to the top. H, I, E, and C is what we have now in memory. The good thing, as you can see, is that the memory is smaller. We don't need to have that much in memory. So H and I, we try, there is no more successes, so we can stop. So we go back. So we have tried H, we've tried I, can do nothing. So then we can explore E. And now we can look at what are the children of E again, J and K, and we add them on top again, J and K, and so do we have E and C? No, E has gone, just C, yeah? And as you can see in each of the steps, the amount of information in the queue is relatively, in the stack is relatively small. So we'll see that in a minute. But the general principle, I hope, is clear. So now the next one we have to explore is J. We don't find an answer in J, so we look at K. There is no answer in K. So now we have C, and we go to the next higher level in the stack. Yeah, and then we go on again. We expand C to get to F. We get to I. We don't find a solution. We have to backtrack to M, and we have to backtrack to H, and then we have looked through the entire search space in a systematic way. So, does it always find a solution if one exists? And the answer is, unfortunately, no. Because what might happen is that in each of the states, if you have a cycle, if you have a way back, you might always end up in the same state. Basically, what you can have is that you have a huge a huge stack, sorry, where when you expand A, you add B, and when you expand B, you get to A again. And that basically means you always end up in a loop. So unless the search space is finite and no loops occur, you cannot guarantee to find a solution. That's the big problem with depth first. The complexity in terms of time is the same because you might have to look exactly at the same nodes that you have to look if you do breadth first search. So we don't win. In many solutions, it's faster, and that's particularly also because we can look for the right path that we explore if we have more information about the system, if we have heuristics that we can apply. So it is the same worst case complexity, but it is a bit faster in many applications. Now the space. The space is good news because instead of having the entire breadth of the tree in memory, we only have to have one branch. And if you think of a tree, then to have all these elements is usually far less than if you just have one path in memory. So basically the order of magnitude that we have here is linear as opposed to exponential that we had before. And that makes a big difference. But the problem is we cannot guarantee that we find a solution, and we cannot guarantee that it's optimal. So that's bad news. There is an incredibly simple and cool solution to this, which I think is one of the magics of sort of research that people looked for, had this problem in the 60s and 70s of the last century. They couldn't solve this. It took them 10 years to come up with this solution. And when you now think about it, it's so simple, it's so elegant, it's so easy. And I'm going to talk about it on Friday. Because I have no time left. So just to be sure that to round this up, we go, can I finish? Oh, sorry, Thursday. Oh, that was a spoiler. If I hadn't, yeah, I shouldn't forget to mention it. If I forget, please remind me. So the depth first means that you go through one of those game situations and you check whether it's a solution or not. And we're going to come back to that in a couple of days. So that is the solution that I show you on Thursday. So don't look at it now. But I can promise you, it has both the properties of depth first search and... Sorry. I still haven't shown my last slide. You can stand up when I show you my last slide. Yes? So I still have 30 seconds, please. So this is the algorithm that I will show you on Thursday. So the summary. I've shown you two of the basic search methods for selection of an agent's choice. So what can an agent do in each of these situations? You have to formulate the goal. You have to formulate a problem in terms of initial situation and from getting from one transition from one state to another. The solution is then a path in the tree, and we do just systematic search in these trees. So we look at these algorithms, we look how complex they are, whether they're optimal, whether they always find a solution, and so forth. And with uninformed search, we only go through all of them. If we have informed search, we take more information with us. And this is what we're going to do tomorrow, to understand more about the processes and see how we can bring this into a game, for example. So in Schnapsen, we use heuristics that guide us through the search process. We have an adversary, so it becomes more complex. We play with partial observability. That's what we're going to do tomorrow. And we play with an element of chance. So that is going to become far more exciting. And here's my last slide. See you tomorrow.